RDMA here, and then at the bottom we've maybe got our iWarp or our InfiniBand or whatever. Okay, I'm not too worried about the bottom one. Whichever flavor you want to use, that's fine. Go for it. Use your favorite vendor. Use your favorite protocol. That's okay. I want to really kind of focus now on the RDMA part and the NVMe over Fabrics part. So what is NVMe over Fabrics trying to achieve? At the end of the day, what it's really trying to achieve is the creation of virtual storage devices on CPUs that don't necessarily have any storage. Right? At the end of the day, what I'm trying to do with NVMe over Fabrics is say, I've got something that does have storage, I got something that doesn't have storage, and I'd like this guy to think he's got storage by providing that storage over a network. Right? There's a lot of different things that have done this in the past, right? Network file systems, iSCSI, ICER, there's many flavors of things that have provided something like this capability. But what we're trying to do is do it at a new level of performance that's more targeted at non-volatile memory than spinning disk. So we're going to focus on latency, we're going to focus on offload, we're going to focus on outliers, we're going to try and make this very efficient. Right? So that's why we're creating something that does what other things have done before, and we're going to try and use RDMA in order to do that. So at the essence of what it is we're trying to do, we're trying to create virtual devices on a host. Okay? And I'm going to show you an example later of exactly how that is. The other thing that we want to do is make it so that this host can talk to this device as if it was a local device. Right? So I can issue NVMe commands against it. Those could be admin commands, like I want to format you, or I want to, I want to erase you. I can issue standard NVMe commands like read and write and compare. Right? I can issue vendor-specific commands. Maybe I can do commands around deduplication or services from a storage-defined network space. Right? NVMe allows vendor-specific command sets that do interesting things. Maybe this is an open channel device, right? That talks in a non-block fashion, but it still accepts the commands because it's tied into the NVMe standard or some derivative of that standard. Right? The host that connects to the physical storage is called a target. So in SCSI land, we have initiators and targets. For some reason, NVMe decided they wanted to call it something different, and these are called hosts. These are actually often called controllers, but I'm going to call them targets because that's kind of what the Linux kernel did. So we'll focus on that. And you'll also notice that there's going to be a couple of places where I have different ways of saying NVMe over Fabrics. I think this is the way NVMe over Fabrics Marketing Committee has decided officially it's going to be called, which is the most god-awful decision ever. So it's NVMe -small o capital F, and I don't think I have that right. The one I really like is NVMF, and that's the one we used when we were writing the kernel driver. So it kind of stuck with me. So you might find, I tried to change it so I'd be consistent with the marketing group, but I don't always do what marketing tell me to do. Much jargon. Right. The interesting thing on this side here is that the storage device here doesn't necessarily need to be NVMe. So basically we're providing storage, and we're providing it in a way that the host thinks is NVMe, but you don't actually have to use NVMe over here. There may be some advantages to using NVMe over here. We'll talk about those towards the end, but you don't necessarily have to. Any block device would actually work there. We'll talk about that too in a little bit. So how does NVMe over Fabrics work? Well, if you go back to where I walked you through an NVMe command, what we're doing is we're taking the 64-byte commands that we were doing for PCIe, and rather than pushing them out over PCIe, we're encapsulating them in an RDMA capsule. Very straightforward, right? It's a classic case of protocol encapsulation. Take a protocol you already know, encapsulate it in another protocol you already know, and now you've got X over Y, right? So we basically have, these diagrams are all taken from the spec. The spec is publicly available, so you can go and get them yourself. And basically, we take the 64-byte command, and we put it in a capsule, as we call it. And then we might, potentially, we don't have to, but we might include some data in there. And the reason why we do that is sometimes it's efficient to put the command and data together, especially if the data is not that super long. Right? So we have the ability of putting together this construct, and then we can send this over our network, and that's our RDMA network, and RDMA knows how to send messages very efficiently. So really what we're doing is taking NVMe commands and putting them into capsules that we send over RDMA. Those capsules will support many different types of commands. We support admin commands, we support standard NVMe commands, we have some commands which are specific for fabrics. And like I said, these I/O command sets, they can be vendor specific. So we can do very generic things of our own choosing if we want to. Or we can do standard based things if we want to as well. Right. If we don't include the data in the capsule, then what we actually include is something called an SGL, the scatter gather list. But it's not a direct memory scatter gather list, it's an RDMA scatter gather list. It's going to refer to these memory regions and offsets that I mentioned earlier. And it's basically going to be a way for the RDMA devices to know where the data is, not in direct memory placement, but in RDMA data placement language. Okay, and that's how we basically put these things together. I am not going to go through this slide. This is basically how an RDMA write would work. If you want to go through this, we need to get more beer, basically. Because this is a very, very, very kind of long-winded kind of, this is the way it goes. These slides will be publicly available. You can go take a look at them, and you can work through them, or we could chat about it over an email. Really,
what was the challenge on this protocol?
What's that?
What was the main challenge here?
Well, there's a couple of. So the question is, like, what are the main challenges of the protocol? I think once we actually decided on the format of the capsules, it was actually pretty straightforward to start putting some proof of concepts together. And John and from Mellanox will talk about many, many, many proofs of concepts that were done. That was pretty straightforward. I think one of the challenges was really in the development of the Linux driver, where we were trying to get more performance out of the system. So it's really understanding where are the bottlenecks, and I'll be honest, there's still work to be done there, quite a bit of work to be done there, and how do we address those bottlenecks? Because there's certain pinch points in the way that we want to do some of this. Some of those pinch points are around taking locks, some of those pinch points are around memory bandwidth issues, and some of them are around scalability for this pinned memory that RDMA requires. And all of those are challenges. And I think all of them are also opportunities for startups to do some interesting innovation in the fabric space.
Can you give some ideas in that?
Well, I'll talk about some of that in just a little bit. Yeah.
Does the doorbell equivalent still work in the fabric space?
So it's not quite the same as a PCIe TLP, essentially. Yeah, so the way that you do some of the interrupt handling is quite different in the current driver. And that's another area where you can innovate, because RDMA NICs are also capable of generating interrupts, right? So there's a lot of games you can start playing here. And so the standard Linux driver does do the standard, and it adheres to the standard, but I think there's other ways you can get to the same functional behavior that may be more efficient. And like I said, I think that's where there's some real innovation. And I know there's at least one person here from E8 Storage, and E8 Storage have they've been involved in this space for a while, and they do things a little differently, and they think that what they're doing is more efficient. And one of their market differentiators is, or one of the things they're trying to sell is exactly that. They've tried to innovate in this space, and they're trying to make a business out of that, which I wish them all the best.
Spec does not define it.
What's that?